Okay, guys, welcome back. And the topic this week is to mix a discussion of diagrams, linked and unlinked, with a second midterm. So we're going to use some of the time today to actually discuss the midterm. And if it's needed, we could actually, after the break, more focus on the midterm and just discuss that and not have a lecture. So this is very much up to you guys. But I wanted to link some of the discussion this first hour to some specific things which are related to the midterm. And then we are going to look at the linked and unlinked diagrams and try to wrap up this part. And tomorrow, if we get there, we will start with the last many-body method, which is a method which is widely used in atomic, molecular physics, quantum chemistry, condensed matter physics, nuclear physics. It's called copper cluster theory. And that's one of the standard many-body methods. Now, a lot of the material here is something which I haven't typed in, especially that on linked diagrams, etc. But Shavit and Bartlett, chapter 6 and 7, they actually contain essentially everything you need to know. And chapter 6 is the one where they derive the linked diagram theorem. And so the linked diagram theorem is, if you do it in time-independent perturbation theory, it's a little bit clumsy, and that's what's done in chapter 6. The topic which we will not cover is time-dependent perturbation theory, which also links with Green's function theories, etc. This is something which we will not cover this semester. But if you're interested, I can direct you to material on that. There's a limit to how much we can put into 10 credits. So linked diagram theorem plays an important role also when we deal with copper cluster theory. So I'm just going to switch over to the whiteboard, and we are going to take a look at some things which are related to the midterm. And one of the topics I wanted to bring up is how do you interpret the results you get from FCI calculations in terms of many-body perturbation theory. And there is an exercise where you're asked to compare your FCI calculations, that means the coefficients you get from the diagonalization, with many-body perturbation theory to second order. And to second order, that means that the wave operator, as we discussed earlier, is to first order in the interaction. So let's remind ourselves about some of these things. And there's actually a reason why I bring it up, because this allows me to catch two birds with a stone, in the sense that we are going to use this when we look at copper cluster theory as well. And there, the so-called amplitudes, as we will define pretty soon, they're actually solved by an iterative procedure. But let's look at what we got to first order for the wave operator. So if we just remind ourselves of the second order, so this is a discussion both of an exercise in the project, and then it also is something which will link with the discussion which is going to come about linked and unlinked diagrams to see how these appear, and also how we can use diagrams to intuitively say whether this will contribute or not to the energy expectation value. So let's do a quick reminder. So if we now look at the second order perturbation theory, so I'm just going to put a set 2 here to indicate that that's second order perturbation theory. That is something which we wrote as a vacuum to vacuum expectation value, where we have the interaction piece. And then we had this Q divided by E0. I'm just going to quickly remind you these different definitions, times phi 0. This term, which you see here, is often called the resolvent. So we define an operator R, and that's simply because that's the inverse of, so this operator here is now given as a sum over all the intermediate states. So with this M runs from 1 and in principle to infinity. So I'm not going to put a limit there because we will always truncate. So mathematically, it should stay an infinity there, but we are not going to have an infinity of states. And this is then divided by an epsilon 0. So this is the unperturbed energy minus an epsilon of m. So this operator then allows us to define what kind of terms we are going to get. And if you look at the action of this operator here, R, on a specific state, if we call this a state n, we know that this one simply becomes equal to this state n, because we are using an orthonormal basis. So we have an epsilon 0, which is the non-interacting energy of the ansatz for the ground state, minus this non-interacting energy for this state n. And normally n, this phi of n, is not equal to phi 0. So n is not equal to 0. That's one of the basic assumptions. So the state is not included. Now, when we then looked at the contribution to first order for the wave operator, so we can actually define then the wave operator, and this is defined as follows. To first order, that is simply the operator R acting on HI. And then this is multiplied with phi 0. So that means that if we now calculate one of the contributions, which we discussed last week, is something which then would look like, and now we're putting in the interaction. So if we now look at the two-particle, two-hole state only, then this operator R, which we have here, is going to pick a two-particle, two-hole excitation. And that means that when we act with H1 on phi 0, we pick a specific two-particle, two-hole excitation. And the term which we got then was equal to 1 divided by 4, which is interaction. We have a sum over the intermediate single particle states. And these actually represent, these guys here, represent, if we go back here, to a specific intermediate state n. Because now we are using, as I said, this single particle picture to build up a many-body basis. And the benefit of that one is that we can rewrite everything which previously was given in terms of many-body states, in terms of single particle states. And that allows us to also be able to calculate the expressions. And here we had a integral, or matrix elements, as we often call them. And this is divided by this energy, single particle energies. These are no longer the many-body non-interacting energy, but the single particle energies, which normally are the non-interacting single particle energies in perturbation theory. Minus epsilon A, minus epsilon B. But then we have a state here, which is now a state like this. So if we now think of the specific exercise which we have and the problem which we have defined a pairing Hamiltonian. And that's a special case because we would also have a contribution where we would have a sum over AI. And that's the one where we produce a one particle, one hole excitation. And that contains now an A of this operator F of I divided by epsilon I minus epsilon A. And this is then multiplied with a one particle, one hole case. But for the project which we have, these kind of one particle, one hole cases, since we now conserve the spin and the number of pairs, then this one is not entering our calculations. So that means that in the second midterm, this is equal to 0. This term which we have here. So the only term which we have then is actually this guy here. This, if we now go back to the diagonalization thing, so when we diagonalize for the FCI case, what we have then is that the true ground state, if we just look at the ground state, is a linear combination over all these Slater determinants. In our case, these are just 6. And we have a sum from I equal 0 up to 5. And then we have the coefficients, the overlap coefficient 0i here, multiplied with the Slater determinant phi of I. So that means that if I now pick one of these could be one of these Slater determinants. So we are looking, when you diagonalize, what you get from the diagonalization is actually these coefficients. So now you can go in, because you have ordered these coefficients according to a list of Slater determinants. So the Slater determinant phi 1 could, for instance, be equal to this one, like that. So that's a possibility. Now, what you need to do then, if you go back to the FCI case, then this specific coefficient, which you see here, that coefficient is simply going to be equal to one of these possibilities which we have, where we now have 1 divided by 4. We have the sum over these intermediate states, A, B, I, J. And then we would have the matrix element, which is simple in our case. It's just a constant. So that becomes a G. And then we would look at the single particle energies and then find the difference between the whole states and the particle states. So that means that we would need to look up that matrix element A, B, V, I, J. And then we have an epsilon I plus epsilon J minus epsilon A minus epsilon B. And then we have the states phi I, J, A, B, where one of these is going to be this one. And then we have, for the two-particle, two-hole excitations, we know that we have 3 more. So you can actually just go into your list of states, the way you've ordered them, and then simply find these specific contributions. And then you can compare these with what you get from diagonalization. And one of the things you will notice then is that when the interaction becomes strong, that means that your numerator here is large, then clearly many-body perturbation theory is going to have larger and larger differences with the exact diagonalization. And you've probably seen that when you started to look at second-order perturbation theory, especially if you increase the value of G. Does that sound familiar? You've seen something like that in the diagonalization? Any questions so far? I mean, please interrupt me if something is unclear. So it means that when you diagonalize, you have everything, and then you can look at how good an approximation this one is. And then you can look at coefficient by coefficient. So that's one way to compare the full diagonalization with perturbation theory. So what perturbation theory is actually to provide an approximation to these specific terms. And you see that this is obviously dimensionless because we have dimension energy here and dimension energy here, as it should be. Now, this has some important consequences for our next step, which is going to be copper cluster theory, because then we are going to set up an iterative scheme where we are going to calculate these quantities here. So in copper cluster theory, what we are going to do then is simply to replace this term here with a general operator, which is going to look like 1/4. And that is an operator which takes into account particle hole excitations. And we're simply going to call this for Tij of AB, and this is multiplied by Ij AB. So the factor 1/4 is now included because this is an operator. And it's an operator which now acts on pairs. And it's a two-body operator. So then we have to make it properly anti-symmetrized. So these elements which you see here now, these Tijs, they become matrix elements, as we will call them, or amplitudes, which are in perturbation theory are given by these quantities here. So copper cluster theory, which we're going to meet tomorrow, if we get time, is now a way of rewriting Schrödinger's equations in terms of nonlinear equations in these coefficients Tij, AB. And this is a set of nonlinear equations which you then solve iteratively. And one famous method for solving nonlinear equations and to find the roots of such equations is Newton's method. And this is a method which is often used to perform these type of calculations. So I just wanted you to see this kind of links because it allows us to link the calculations we do with an approximative method with the exact one if you can diagonalize exactly. So to diagonalize a problem is a luxury approach because normally you have to reduce your Hilbert space considerably to be able to diagonalize. But if you can diagonalize and that effective Hilbert space is meaningful, then you have the exact answer. And then everything else we do is approximations. But normally you prefer the approximative methods because your Hilbert space is so large that you cannot diagonalize. And then you need an approximative methods. And perturbation theory is just a way to bring in these contributions order by order. So when you compare your FCI calculation, the only thing you need to do then, if you look at the ground state here, and it's sufficient to look at the ground state in this midterm, then you would simply pick these different terms and find out their values and compare them with these coefficients C, 0, I. And you know that we have only, in our case, we have only 3 more states here of this 2-particle, 2-hole type. And we know also that the 4-particle, 4-hole gives 0 contribution. So in our case, we have only 2-particle, 2-hole. And also to second order, in the energy, we don't get more than 2-particle, 2-hole excitations. And like we discussed last week, if you wanted to have 4-particle, 4-hole excitations, you need to go to 4th order. And you will see specific diagrams in perturbation theory, which are to 4th order. Okay. Any questions? Does it sound clear? So have you reached this point in the midterm? I see some people are nodding their heads and some people are not nodding their heads. Okay. So how do we represent this diagrammatically? Because we are used in a way to represent this in terms of dotted lines. So what is pretty common now, if you look at this one diagrammatically, is to represent this in terms of different notation. So instead of having the one which we have seen before, which looks like this, so this is the interaction, and then we create a 2-particle, 2-hole piece. It's common to actually replace this one with a bar to indicate that now you have, it's not the bare interaction which you have, but the interaction divided with an energy denominator. So you would typically indicate it like this, and then you have the 1-particle, 1-hole pair here, and then the other 1-particle, 1-hole pair. So this is an A, a B, sorry, this should be a whole line, then an I, and a J here. So this is a typical way by which you would then set up the whole contribution. And then we know that the energy itself, finally the energy is actually given by phi 0 HI, and then we have this resolvent operator. So we wrote this in a more compact way, and this is given by this term here. So that means that at the end, we have an interaction piece at the top, which is now simply this term here, which acts on the ground state. So this is reflected in this one. And then we perform the contractions because now we have an operator for the intermediate state. And this term, which you see here, is actually given by creation and annihilation operators. So in this term here, if we just write it out, there is an A dagger, an AB dagger, an AJ, and an AI here. So you're writing this out, this intermediate or the wave operator to first order in the interaction. We write it out as an operator because that is what it is. It is actually an operator. And then when we do the drawings here, you could now think of this as bringing together these 2 different pieces. And this is what we have done before. So we perform the contractions because then we have the 2-body operator here. And that gives the final diagram, which we can write like this. This is one way of writing it, but it's more common now since it's second order the interaction. So this is less common. We would then write it simply like this. and then we have an energy denominator which has to be included explicitly. And that energy denominator comes from the difference between the particle and whole lines here. So this is a typical diagram which we also discussed last week. Now, if we then go to more complicated terms, we can now look at the second order in the wave operator. And let's try to do that and see what kind of contributions we can get to second order in the wave operator. But before we proceed, I mean, are there specific things with the midterm which you would like to bring up? If there are some specific things connected to this exercise, or whether this exercise was pretty clear. No, yeah?
I was wondering if it was, I was a bit confused about how it was worded. If it was, how does the second order wave operator look? Or if it was...
I think it's the first order wave operator.
Yeah, which is the second order contribution.
Yeah, to the energy. So because if you look at the contribution to the energy, this contribution to the energy to second order is given by this term, but then the wave operator to first order would then be given by this term here, because it's actually this term when it acts on HI and phi 0 that it picks out a one particle, one hole, or two particle, two hole excitation. And in our case, since we have limited the Hamiltonian to be a Hamiltonian which only acts on pairs, and actually one thing you could do if you want to, but this is not something which we have asked for in the project, you can actually simplify the calculations here. And in some cases, you can even visually look at what kind of contribution should be there. Because if you look at, for instance, this contribution here, then you can simply pick out which one the pairing operator will act on. So one thing which what you can do, and we didn't ask you to do that, is to show that the Hamiltonian itself commutes with a pairing operator which you have defined. So in the first exercise, you're simply asked to look at the commutation relations between the pairing operators and that they commute. Now, one thing which would have been a little bit more involved, and you would have been less happy with me. You're probably not that happy with me anyway, because I tend to give all these exercises, but is actually to show that the Hamiltonian commutes with the pair creation or pair annihilation operators. And that shows you that the number of pairs is a conserved quantum number. And the way you would do that first, if you look at the one body part, is to rewrite that in terms of the number operator. And the number operator, because the one body part is just A dagger A, and that is simply the number operator multiplied with a constant. That commutes with the pair operator. And then you have the second term, which is the interaction, which just contains P dagger P, and that acts on when that's also a term which commutes with the pair operator. So then the total Hamiltonian does not only conserve spin, but it conserves also the number of pairs. Then what you could have done, if you want to simplify this specific case, but that's something you would tailor to the case of only no broken pairs. Then you could have reduced this problem from 4 particles to 2 pairs. And instead of having 2 particles here, you would just have a pair here and a pair here as an object. And then your Hamiltonian would be like a one-body Hamiltonian, where instead of having, if you think of a one-body Hamiltonian, we have something like A dagger I, AI, but now you would have a P dagger I and PJ. And that would be an operator which just acts on one pair at a time. And you could think of that as a one-body operator or one pair operator. That normally simplifies the calculation, but it's something which is often a case tailored to this simpler case where you don't break any pairs. So you could, if you run the calculations like that, that would also give you a full score on the exercises. And it simplifies things also when you do many-body perturbation theory, because then, in this case, these states which you see here would then simply be replaced by two different pairs. So this could be a pair, and this would be a pair. And then your Hamiltonian would simply be given by this one acting on a specific pair. So you see the connections. So it's one way of doing the exercise, but we haven't, we haven't discussed that. But you should feel free to use this kind of properties of the Hamiltonian and the pair creation operators and annihilation operators. So any further questions? One thing which I also wanted to bring up, if we still stay with the first order in the wave operator, if we have the one particle, one hole case, what we have then is that this operator is something which we would write like this. So we have an A and an I, and then we can put this bar here to indicate that now we have created a one particle, one hole case, but where this one is actually given by the sum of A and I, and then we have this specific integral of epsilon I minus epsilon A. So that means that, and this is then acting on a state of a one particle, one hole character. And a typical diagram which we ended up with is a diagram like this, an actual case which now contains the one particle, one hole contribution with a bystanding vacuum, which now produces a mean field here. Now, this specific case is something which is also interesting for the problem which we have at hand, because in our case, we cannot produce any particle hole excitations. This has also consequences for the one of the exercises when it comes to the Hartree-Fock calculations. Actually, for Hartree-Fock, you can write in just that exercise is you realizing that you are already in a Hartree-Fock basis. And you will see that if you set up the first iteration, your Hartree-Fock algorithm stops at the first iteration. So that means that your Hartree-Fock energy is simply the unperturbed energy minus the strength of the interaction, G. That is your Hartree-Fock energy. And you see quickly then that since you don't have any particle hole excitations, you don't allow that, then your Hartree-Fock stops at the first iteration. And you will only change the energies of the hole states, because these are the only ones which get contributions from states below the Fermi level. And you can see that quickly when you look at both these diagrams and also the kind of Slater determinants you have, because when you now look at the system, if you have particles here, you know that in the Hartree-Fock calculation, you would have an I of F of I, which means that you have the single particle piece H0 of I. So for the whole states, this contains now a sum over these bystanding particles, Ij of V, Ij. And in this case, you can have if I is equal to this one, so let's mark it like that, then clearly a bystanding particle, if that is included here, then this interaction matrix elements gives us a non-zero contribution. If, however, the whole state is given by this one, then we are breaking a pair and the interaction piece gives us zero. But then you see that the energy here will quickly be equal to epsilon I and minus the strength G, because there's only going to be one which contributes. So then you have immediately the Hartree-Fock energy. And if you then look at the iteration which you can make, and where you mix particle states, then you see quickly that due to the property of the interaction, this is going to be zero. So you're already in a Hartree-Fock basis. And that means that there's essentially almost no calculations with that exercise. Any questions? So I'm not going to solve everything, but I wanted to discuss these things because there are lots of I'm pretty fond of this exercise because it gives you a lot of intuition about many-body systems with a simplified Hamiltonian, which is also somewhat realistic in the sense that pairing correlations are fundamental in many physical systems like nuclei, atomic nuclei. And also this pairing model was proposed by Badin, Cooper, and Schrieffer to explain superconductivity, and they actually got the Nobel Prize for this simple Hamiltonian. So it's a widely used example in physics. Now, I wanted to say a little bit about the wave operator to second order, unless you have any questions about the project, because the wave operator to second order is going to bring in a subtlety, which always confuses people in the beginning. And that's the topic of linked and unlinked diagrams. And later, there is a theorem which is called the linked diagram theorem, which is the one which saves the day when we are doing many-body perturbation theory to higher orders. So if we look at this wave operator to second order, so let's do that. In that case, we have a psi of 2 here, which is given by this resolvent operator of an hi multiplied with r times hi with phi 0. So we are still doing many-body perturbation theory on a non-degenerate ground state. There's nothing, however, which hinders us to look at more than just one state. But our model space, the effective Hilbert space, is just phi 0. And the rest is then taken into account by these higher order excitations. Now, one operator which you would get then, when you have 2 interactions, a typical diagram which you may get, is a diagram like this one. And we looked at that last week, but we didn't analyze it in terms of the wave operator. So we would have an interaction here. So these are particle states. And then we can think of this thick belt here, which now also includes an energy denominator. But it's pretty common to, unless we do copper cluster theory, it's actually common to, in many-body perturbation theory, to drop this bar and just use the interaction itself. But when we come to copper cluster theory, because then this, if we go back a little bit here, when we do copper cluster theory, we are going to sum this 2-particle, 2-hole contributions to infinite order. So that means that we are not going to have only a plain second-order interaction, but there will be more than just a first-order term here. So because you have ways to resum contributions in many-body perturbation theory. And some of these can be resummed as geometric series. So that means that this bar is often left to represent a summation of more complicated contributions to either infinite order or to a given order. When you diagonalize, you're actually producing in here many-body perturbation theory to infinite order. So when you do perturbation theory, you have a correction here from second order. Then you have first order interaction, then you get second order, etc., etc. And the correction to second order, where you do a 2-particle, 2-hole state, is actually this one. So this is a 2-particle, 2-hole state where you now have added one interaction line. Because you can see that when you now write out the wave operator for this one, this is going to give us, if we now look at the diagram rules which we have, so we have 2 whole lines, so that gives us a factor of +1. We're going to have 3 equivalent pairs, which we're going to see later. So this gives us a factor of 1 divided by 8. And then we have a sum of A, B, C, D, and I, J. And we are going to get, if we now put labels C, D, and A and B, and I and J here, we are ending in a state CD for the particles, V, A, B, and then we have A, B, V, and I, J. And I'm skipping this anti-symmetrization sign. So we have an epsilon I plus an epsilon j minus epsilon A minus epsilon B. And this is then multiplied with an epsilon I plus an epsilon j minus epsilon C minus epsilon D. And finally, it is multiplied with the state which we are producing as an intermediate state. So this is a two-particle, two-hole state. So when we now have propagated, so we create a two-particle, two-hole state here. We propagate these two guys, and then these two guys get de-excited or into a new state, C and D here. And so that means that this diagram here produces this as an intermediate state, but it is a contribution to second order. So if I now want to go to the wave operator and the connection with the FCI, and you can see there's a reason why I didn't ask you to compare the wave operator to second order with the FCI, because there are many, many more diagrams. So the second order piece to the energy, which means the first order to the wave operator, has just one term. But now we can get many terms here. And this is just one of them. And then we can produce more excitations, because at the end, we are going to contract this. So we have a two-particle, two-hole piece. But when we calculate the energy, we're actually going to have to contract it with something like that to bring us back to the vacuum state. So if we now look at further example to the wave operator here, we could now have a diagram which looks like this for the wave operator. So this is a particle state, but now I'm putting a whole state here. And in this case, I'm not having any equivalent lines. So this is a state I, this is a state A. I have a B and C, and then I have a J and K here. So if I look at that wave operator, that's going to have a sign minus because I have three whole lines. I'm summing over A, B, C, and I, J, K. The upper vertex is a particle state going out to the left, a whole state K going out to the right. I have a particle state B coming in and a whole state J coming in to the right. And this is multiplied with a particle state B going out, a particle state A here. And then I have a V, and then I have a whole state I to the left and a whole state K to the right. And I'm skipping the anti-symmetrization sign. And this is going now to be given by an epsilon I plus an epsilon K, the whole lines, minus epsilon B minus epsilon A. So that's the first intermediate step here. And then we have the next one where I have an epsilon I plus an epsilon J minus epsilon C minus epsilon A, multiplied with a new state. And this state which we produce is also two-particle, two-hole state, but it has been produced in a different way because the intermediate excitation is of this intermediate excitation which you see here is also two-particle, two-hole, but I'm ending up with a one-particle, one-hole here and a one-particle, one-hole state here, which is a little bit different from the one we had previously. But when we do many-body perturbation theory, then we get all these different contributions. So this would be a state where we now have a incoming state, IJ. That's the whole state. And then I have my outgoing one, which is now a C and A here, the way it's drawn in the diagram. Then you see that I can always interchange states here. I can interchange A and B. That takes away the minus sign. So you can always manipulate this so you have the equation with a specific coefficient here. But this is also what you see here, a new two-particle, two-hole state. Then we can continue this exercise and we can produce more complicated diagrams. So we could actually have a diagram which looks like this. So let's just show examples here of contributions which you get to the wave operator. So at the end, you would have to contract this wave operator with a final interaction piece. because the total energy, as you can see, is now, if you look at what you have here, when you make the contraction, there's a phi 0 with an h of I, which comes in here. So that has to be contracted with what is being produced by this chain of interactions. And as we discussed previously, perturbation theory gives you this kind of pseudo-physical way of thinking of things. Like you have the two-particle, two-hole interaction, which is being created. This propagates in the system. It interacts with other bystanding particles. It produces a new two-particle hole excitation, and then it continues like this till you go back to the ground state and the system gets de-excited. And in principle, you're summing these contributions to infinite order. So another diagram which you can get is a case which we also have seen partly before. So we can have a whole state here. Let's label this as an I. And then we have a particle state A here. And then we produce this diagram. And we have a particle state here. So we will put labels C, and let me just put a B here, and a C here, and a J here. Now, we know that when we are going to make the final contraction here, we can have a term which looks like this, or we can have a term like that. And as we've been discussing before, in our specific case, for here, we create actually a one particle, one hole intermediate state. And that means that that can only be matched with a one particle, one hole state here, which de-excites the one particle, one hole states back to the ground state here. So that means that this contribution here, if you look at the diagram, what you have produced an excitation of the one particle, one hole type. And to third order, this specific contribution here has to be matched with this one in order to bring us back to the ground state of the system. So this is then a type of excitations which you produce. Now, if you look at this expression here for the diagram, we would now have two pairs, one pair of particle states, B and C, which are created at the same vertex and are destroyed at the same vertex. And that gives rise to a factor of a half. We have one closed loop, and then, so one closed loop here. And we have one whole line and one whole line here. So that means that two whole lines and one closed loop. So that's giving rise to a sign of minus. Then I have the summation over the states A, B, C, and then I have my ij here. And if I set up the matrix elements now, I have, for the upper one, I have an outgoing particle state A. I have an outgoing whole state J. I have an incoming particle state to the left, B, and an incoming particle state C to the right. And this is multiplied with the next one, where we have an outgoing particle state B, outgoing particle state C to the right, and then the left whole state and right whole state. And then the energy denominator, if I now take this line here, then this is going to give us now an epsilon I plus an epsilon J minus an epsilon B minus an epsilon C. And the final one, which is this one, before we make the final contraction here, is now going to be given by simply epsilon I minus epsilon A. And this is multiplied by the final state, which we have after all these excitations, which is now a one particle, one hole state. So before we take a small break, we are going to look at yet another contribution, which will not contribute. And you will see why this will not contribute. So I can create a intermediate state now, which looks like this. So I have an I, I have an A, an I, and then so I'm just going to set up the diagram here. So I could compute a contribution to the wave operator of this type here. And this has an L, a particle, and then I have a B here, and I have a J and a K. So if you look at what we have created here, this is going to have some intermediate. I'm just going to put up the summations A, B, C, I, J, K, L. And then we have all the matrix elements. But you see now that we produce a state here, which is of a free particle free hole excitation. So I have an A, B, C here. So this is a free particle free hole excitation. And when I multiply this with the phi 0, with h of I, and if h of I is at most a two-body operator, I will at most have something like this, which I can produce from this guy here. And that means that if I now try to link legs here, you see now that this is a two-body operator, and this is actually a free-body operator, because this will contain free particle creation operators and free hole annihilation operators. That means that when I take the final expression here with this one multiplied with this one, this is going to give us 0. So we cannot have a free particle free hole excitation as the final one before we compute this contraction. And you can actually also produce 4 particle for hole excitations, etc., etc. But then we have to be a little bit careful with what type of interactions need to be included here. Okay, so these were just examples. And after the break, I wanted to then discuss this concept of linked and unlinked diagrams, and also bring back that discussion we had with the example from last week, where we looked at this simple two-level system, because that produces also unlinked diagrams.